Hi, welcome back. We've been looking at the skills that are important for doing science, the science toolkit, if you like. Now, what we've done so far is we've identified that the thing that makes science different is doing investigations. When we do investigations, we need to understand what the idea of a variable is. Variables all have values that we can measure or we can describe. What we've said in this last little section when we were looking at the experiment of a pendulum is that we need to make sure that all our experiments, all our investigations are fair tests, which means that we have one variable that is changing, which we know is the independent variable, and one outcome variable, which is the dependent variable. Now, if we want to describe the relationship between these variables, there's a way to do that. Sometimes we represent these relationships, we collect the data in a table, and then we can start to put those values, which we are collecting, those values, those measurement values, into a graph. We can then describe the relationship based on what we see from the graph. So I'd like to do another idea. I want to show you something else. You don't have to learn this experiment. This is a technique of just describing relationships. So here's a spring. There are springs all around us. They do fascinating things, and they used to be really important. They're not as important now. But what we recognize is if we hold the edge of a spring, by applying a force, we can get the spring to increase its length. In other words, we can get a spring to stretch. Now, this one is quite a stiff spring, whereas other springs you might be more familiar with are quite easy to stretch. And they will, with a very little force, be able to give you a long length. Now, a very famous scientist, a man by the name, with the surname of Hooke, he did some experiments in terms of measuring the relationship between the force and the increased length of the spring. So I'm going to talk about the variables involved here of stretching a spring. And what we're recognizing here is that if we've got a spring, and we're going to stretch it, it's going to require a certain force. The thing that we are doing, we are changing. We are applying different amounts of force. So this is your independent variable. The distance above its increased length that it stretches, this is how much further it stretches. So when there was zero force, it's at its zero. The spring itself isn't 0 centimeters. The spring has a certain distance. This is the distance of its stretch. It's above its original length. So zero force, its original length. Now what we're doing is we're saying, let's increase the force. Let's have a 10 Newton force. What's the length? It's increased by 2 centimeters. And then we do 20. It's increased by 4 centimeters. And what we recognize is that as you go up and you increase the force, you increase the distance that it has stretched. So this is known as the dependent variable, because the amount of distance that it's increased is dependent on the size of the force that you've applied. But notice there's a pattern that exists here as well, that if we say take that as our original first one, 10 newtons, it stretches by 2 centimeters. If we double the force, that means we've gone to 20. Notice what's happened to the stretch. It's gone to 4. So in other words, we multiplied this by 2, doubled it, and this one doubled as well. They've not just increased. It just didn't go up 2 and 3 and 5,5. It's gone up in a pattern. And so let's test if it happens again. So let's do it this way. Let's say, what happens if we double the distance here? Well, 4 times 2 will give us 8. Let's compare this value here to that value over there, and you can see to go from 20 to 40, you've also multiplied by 2. There seems to be a pattern emerging, that as you double the one, you're doubling the other. They seem to be increasing, not just increasing randomly, but according to a pattern. Now, That is a special pattern. In this case, as you double 1 or you multiply the 1 by a certain number, you multiply the other value by the same number. So the value of one variable multiplied by 2, you have to take the other value of that second variable and multiply it by 2. The pattern continues all the way through. And you can see that there's a consistency here. One way to test this is to say, well, hold on, let's see if we ask a question about the relationship in this way. Instead of doing a multiplication, let's take a look at the ratio of distance over force. So I'm going to put in another line over here, and I'm going to say, let's take the distance, and I'm going to take the force over there. And if I take distance over force, then I'm going to say this is 2 over 10, which is going to be 0,2. And 4 divided by 20 is 0,2. And 6 divided by 30, 0,2. There is a constant ratio between the distance and the force. They seem to be consistent all the time. So if we take 10 over 50, we'd get 0,2. Now, that has a special relationship. And you can do it algebraically like that, or, as I said earlier, we can plot a graph. I'm going to just sketch a graph here because I want to put in the important parts of drawing a graph for you. So when you draw a graph, you usually will use graph paper or squared paper, blocked paper. You'll need to draw in your axes. Make sure that you've got your axes. That one doesn't look very straight, so let me just redraw it. Put in the axis over here, the horizontal axis. And here's the important thing now. We're going to have to decide, where does each of these variables apply? Well, as a rule, we put the independent variable, the one we change, force, on the horizontal axis. Force in newtons. And this is the distance, the stretch, the extra distance. And we say it's in centimeters. I suppose we could change it to meters if we wanted to, but I'm not going to worry about that just yet because we'll need to add some detail here. Now, when we've got a graph like this or set of axes, we're going to need to determine a scale. And it's really important that you take note of the values and that you plot the values on your graph paper according to even spacing, according to a scale, so that they all fit in. You don't want your graph to be too small so you can't see, and you don't want it to be stretched out. It must be evenly spaced. So let's have a look at the force values. We went up from 0 to 50 and we were evenly spaced. Now I'm not going to be able to do that because I'm just going to put 0 and 50 over there, and I'm just going to do it freehand. 10, 20, 30, 40, and I'm going to move that 50 and bring it a little bit closer and say that one can be the 50 over there. Now I've tried to do it as evenly as we can, and then over here we're going to go to 0 to 10. So we're going to say don't skip out any numbers, make that 10 at the beginning, make that 1, make that 2, make the middle there 5, that's going to be 4. You don't want to squash things up, that's why they must be even. So this one will be 6 over here, 7, 8, 9, and so on. Now, once you've got your scale all sorted out and you've set it up so that these spacings are even and they're all nicely set out, you can use a ruler to do that. You can then go about plotting your points. Now notice this one is 0, 0. It's a very, very important point. When we have a special relationship that I'm going to describe like this one, it will always pass through the 0, 0 point. Now for 10 newtons, we got a stretch of 2 centimeters. So when you go to 10 newtons, you go up over here and you plot a point over there in line with the 2. Now, You can plot points, and that's a maths thing. I'm not going to carry on doing that. I'm going to plot one more point on this graph, and then I'm going to draw a line that will fit through the points as best as they can. In this case, it will be a particular shape, which I'm sure you can all already see. 10, 10 over there, and 50 over there is going to give me a point somewhere over there. And I'm going to use a line to join these points. In most cases, you'll be able to use a ruler to draw through the majority of the points. This is known as a best fit line. In this case, if we now go and see, you'll see that roughly 20, 30, 40 will be over here, and so on. They will form a straight line. A straight line passing through the origin will give you this sort of relationship. The relationship has a special name. We say that these variables are directly, we say that the special name for this relationship is directly proportional. Now, in maths terms, what we're going to do is we're going to say, let's put D for distance and F for force, and we're going to say distance is directly proportional to force. Now, there is another way of representing that. Instead of putting that funny sign, which means directly proportional, we can recognize that for this particular spring, we can make a constant here. The distance over force relationship gives us a constant. You should see from the graph, the gradient of this line here, the gradient is the distance over force, and because it's a straight line, it is a constant. So what we can do is, instead of writing it like that, we can say, well, distance, instead of it with the proportional sign in, we can say distance is equal to a constant times the force. So in that way, we've got a way of describing. We've developed an equation to describe the relationship. What Hooke did, he actually said force is equal to 1 over that constant times distance. So you can write it around in the other way, just making force the subject of the formula divided by 1 over k. It's still a constant. This is known as the spring constant. You don't have to know that, but I just want you to recognize you come up across science constants in many equations, and that's what it's telling us, that when two variables are directly proportional, that we can say this one equals that one times a constant. And it's because we've got this particular type of relationship, directly proportional. Now, there's a second type of relationship that's not directly proportional that I want to deal with now. So let's move on to that quickly. And here we go. Electric circuit, resistance and current. Notice here there is a trend. And we're going to say we're controlling the resistance. So this is the independent, and that's your dependent. We're going to control the resistance. What's happening to the resistance? The resistance is increasing. What's happening to the current? Oh, notice here it's decreasing. But that's not a very strong relationship. As the one increases, the other one decreases. Although it's true. But what we recognize here is that if I double this one, so I multiply this one by 2. 2 times 2 is 4. What happens to this one? 12 to 6. I didn't multiply by 2, but I multiplied by a half. So this one is a reciprocal. These are reciprocals. The one is 2 over 1, and that's one's 1 over 2. They're inverses of each other. So the relationship here, let's test it. Let's try another one. 6 goes to 12. That's also multiplied by 2. Let's see what happens. From 4 to 2, multiply by half. Oh, looks like we've got the relationship. This isn't a directly proportional relationship, but it's known as inversely proportional. Now, when you plot this graph, you don't get a straight line, because as the one increases, the other's decreasing. We're going to plot the independent variable and the dependent variable in the same way, but we won't get a straight line. What I also need you to recognize is that if we take 2 and 12, and 4 and 6, and 6 and 4, and 8 and 3, and 12 and 2, and 16 and 1,5, we start to think about, well, what happens if we put them over each other? Doesn't seem that the number is getting the same. But what happens if we multiply them together? 2 times 12 is, well, you've got it, 24. What about 16 times 1.5? Well, guess what? It's also 24. And 2 times 12 over there is 24. It looks like if we multiply resistance times current, we're going to get a constant. These two, resistance and current, then are inversely proportional. And we'd say R is not directly proportional, but is directly proportional to 1 over I. So that's how we represent inversely proportional. We do the 1 over because of the inverse idea. Now the graph, just quickly, and I'm not going to plot all the points, I just want you to see what this graph will look like. If I put resistance and current, and I put current in amps and resistance in ohms, then the graph, starting with a large resistance, will have a low current. It will look something like that, a curve. That's not very helpful. So what scientists do, what physicists do, is they say, well, let's do a 1 over relationship. And that's exactly what they do. They say, let's, like I've done over here, let's do 1 over I. So what we'll find is we do R and 1 over I, and now you'll get a straight line. So what we're saying is R is directly proportional to 1 over I. Now, you can go and try that. Do a plot. Practice your graphing. It's one of the important skills you're going to need. But I think it's really important that you know and you understand those two relationships when we're dealing with investigations. Learn to identify directly proportional and inversely proportional relationships. Okay, now we're moving on, and the next thing we're going to go to is the idea of some math skills that are really important. We're just going to conclude today's lesson by looking at some math skills. Here's a question for you to think about. Is there a difference between 6 centimeters and 6,0 centimeters? Think about it carefully. I think you need a short break. While you're thinking about it, have a break, have a stretch, have a glass of water. I'll see you in a bit.